Right. Yeah, thank you so much for the invitation and thank you for coming. So I'm mostly going to be talking about some work of Hahn, Raxit, and Wilson today. Um, so to start, let me just do some setup in the setting of filtered spectra. Some of this I did talk about in the previous talk, but just in case you weren't there. So what are filtered spectra? So by a filtered spectrum, I just mean some sequence of spectra like so. There's no conditions on the maps. Don't worry about that. And we're also going to look at graded spectra where we just forget that we had maps. So a graded spectrum is just this data. And each of these are symmetric monoidal. So given I and j in filtered spectra, then we can form the Day convolution. And the value of that on n is the colimit over I plus j greater than or equal to n of I slash ij or jj. And you can do something similar in graded spectra. And then it really looks like the kind of graded tensor product. So this should be somewhat familiar. Okay, so these are symmetric monoidal categories. And then there's a functor or star going from filtered spectra to graded spectra. And this is symmetric monoidal. It's also a left adjoint. I don't think we will use that though. Okay, and then there's a particular way of producing a filtered spectrum that we also talked about last time, which is using the Whitehead tower. So that goes from spectra to filtered spectra. So this had the property that, so recall that how going to n of x, the homotopy groups of that were the homotopy groups of x, star is greater than or equal to n, and 0 otherwise. Okay. And the key point here is that this is actually lax symmetric monoidal. So this restricts to a functor from algebras or commutative algebras in spectra to commutative algebras in filtered spectra, where now we're thinking of these as just monoids in filtered spectra using this symmetric monoidal structure. Okay. And one other thing I just want to mention is that we could have put some integer here. And we would still get the same properties. So if we just do this, the double speed or the triple speed version of this, then we still get these properties. Okay. So this is the background we need to define the even filtration. And now, so the idea is you want to kind of mimic the idea of where you would take some R module and resolve it by like some projective resolution or injective resolution, let's say to compute X. Except now what we're going to do is we're going to start with a commutative ring spectrum. So yeah, let's put this here. The idea is to resolve a commutative ring spectrum by so-called even commutative ring spectra. So what do I mean by that? I mean that, so a spectrum X is even if when you take the 2k minus 1 homotopy groups of X, this is 0 for all integers. And then I'll say a commutative ring spectrum is even if the underlying spectrum is even. Okay. All right. Then we're going to have several different flavors of this, this idea. The first one is the following. So this is a definition of the even filtration. So given a commutative ring spectrum A, then we define the even filtration of A to be the limit over all maps from A to B, where B is a commutative ring spectrum and B is even. And then we apply this double speed Weyad-Tower to B. So this is some filtration on A. I won't really discuss this, but you actually need some hypotheses to make sure that it actually converges to the homotopy groups of A, or converges to A and things like that. But in the cases we will look at, it will be the case. And then we write Eve of A for the associated grid. So in this sense, so if you apply this functor to this filtered object. And I just want to point out that this is actually going to, because of this fact, this is going to take values and commutative algebras in filtered spectra. And this is going to take values in commutative algebras in graded spectra. Okay. So that's the first observation. And then once we acknowledge that, then we could have said, well, actually, this is always going to be a module over Phil Eve of the sphere. So in fact, we can even do better. In fact, this is going to be commutative algebra in modules over Phil Eve of the sphere inside of filtered spectra. And similarly, this is also going to be in modules over Eve of the sphere in graded spectra. Okay, so for what I want to do in the next lecture, I'm going to need a variant of this, another variant of this kind of filtration. Well, actually, a couple other variants. So let me just get those. So now suppose that A is a commutative ring spectrum. And M is an A module. Then we can define filtration on M, which is kind of depends on A. And this is the limit over all maps from A to B, again, where B is a commutative ring spectrum, B is even. But now we apply this to M smashed over A with B. And then the associated graded is for Eve over A of M. And as you can probably tell, if you plug A into here, then you just get the other filtration that we talked about. But of course, this one in general only lands in filtered spectra, or I guess let me just right away say this lands in modules over Phil Eve of the sphere and filtered spectra. And similarly, this is in modules over Eve of the sphere in graded spectra. Yes. Sorry? Before doing this? I mean, this is the definition. You take the limit in commutative algebras. But then you just note that this was symmetric-conoidal. So that means that this lands in algebras. And then because every one of these, because A is a module over the sphere, then you also land in algebras or algebras over the sphere, over the sphere. Does that make sense? Yeah. So yeah, we actually need one more variant of this. Let me try and be quick about it, but if A is P complete and M is P complete as well, we say additionally. So just don't want to write out these hypotheses again. Then we can form the same thing. But there's just one extra hypothesis we need. So B is going to be a commutative algebra. B is going to be even, but then also B has to have bounded P torsion. Yeah, I want to, what, sorry? Yeah.
Left-hand board. You start a mod module over that.
Yeah, that is also true. Yeah, that's true. Yeah, thanks. Yeah, thanks. Yeah, so there's a variant of this where we include a prime, we P complete everything, and we just have to add a bounded P power torsion here. So let me not go into too many details. But I will actually use this version at one point as well. So. Okay, so this is nice. There's a definition. But we're taking the limit over all maps from A to B, whereas B is even, right? That's kind of huge. So this is, it's not so clear from this description how you would actually compute this. Right, so you'd like to have some kind of smaller resolution, like just like in homological algebra, maybe you'd want to work with like a minimal resolution. Although this is still going to be kind of a bar resolution, but whatever. Okay, so to actually compute with it, we're going to need some kind of like nice notion of covers. So if you're thinking about this in kind of algebro-geometric terms, and you had some Grothendieck topology, and you want to think about some kind of nice covers. So the nice covers that we're going to work with are evenly free maps. So map of commutative ring spectra from A to B is called evenly free if for all maps from A to C of commutative ring spectra such that C is not equal to 0 and it's even, then we can form C smash over A with B. And we ask that this is a wedge of even suspensions. So I should say it's a non-zero wedge of even suspensions of C. So these are going to be our nice notions of covers. I chose this definition because it works in all of these different contexts. There are specific notions for the p-complete context, and there's a weaker notion you can use in this context, but just to not introduce too many definitions, I'm just going to work with this one. So now I would like to convince you that these evenly free maps show up very commonly in nature. So So first of all, maybe one of our favorite maps of commutative ring spectra is the map from the sphere spectrum mu. And this is evenly free. So this is just the unit map. So how do you see that? So if you take some even E infinity ring, so that's going to be the same as a map from the sphere into some even E infinity ring. So let's say C is some non-zero even commutative ring spectrum. Then if you have an even commutative ring spectrum, then it's also complex oriented. So I'm not sure exactly how much about this story Viglik talked about, but let me just sweep some things under the rug. But so it's complex oriented, and one thing that you get from that is that this can be computed as as C star, and then certain classes B1, B2, and so on. And then you can use this to produce maps from even suspensions of C into this, produce an equivalence, and then you get that this is a non-zero wedge of even suspensions of C from that. So this is an evenly free map. This is one of our favorite evenly free maps. You could also look at the map from THH of MU to MU. So because this is a commutative ring spectrum, there's like a co-unit map from THH of MU to MU. This is evenly free. So here, we use the fact that THH of MU is MU star, and then exterior on certain classes, I'll call lambda 1 prime, lambda 2 prime, where these are in degrees 2i. So this computation, I think, will show up, 2i minus 1. So I think this computation will show up in one of Samik's talks, and I'm not going to give the computation. Okay, but so basically this is exterior over mu, and then you compute, when you compute C smash over THH of mu with mu, this is going to be divided power. Well, the associated gradient of some filtration on it is going to be divided power on even degrees, and that's going to be enough. Yeah, let me not say too much, but so this is going to be all you need to show that this is a wedge of even suspensions of C. Okay. So these also showed up, this kind of idea also showed up in the work of Bott, Morrow, and Schulze. So let's say, so if R is a quasi-symptomic ring, so here the idea is quasi-symptomic rings are rings that are given by some kind of like polynomial extension and then some quasi-regular quotient. So you're supposed to think of taking some big ambient space and then cutting out something from that ambient space. And we also asked that this map is smooth or is flat. So when you're cutting away from the ambient space, you're doing it in a kind of a similar way as you go around. So this is like a portmanteau of the word temnine, meaning to cut, and sin, meaning like to do it in a similar way. This is according to Barry Mazur, who coined the term. But explicitly, you asked that R has bounded p-power torsion for all p. And if you take the kind of like algebraic cotangent complex, derived cotangent complex, then this is concentrated in degrees 0 and 1. But yeah, let me not go into too much detail. The point here is that what you can do is you can take R and you can form a polynomial ring on the elements in R that has a surjection onto R. And then you can add in all p-power roots of these elements. And then take the push out. And then we're also going to p complete. So yeah, maybe I'm also going to assume that R is p complete to simplify things. And then the point is that you get a map from THH of R to THH of S after p completion. And this is going to be even, and this map is evenly free. So this is another place where it arises in nature. Yeah, here also this is even. And of course here, this is even. And that will also be useful. So yeah, so there's one. Yeah, maybe I'll stop there. I have several other examples, but I think this will suffice for now. So the point here was that these evenly free maps are supposed to be useful for computing the even filtration. Let me leave this definition on the board for now. So this is the theorem of Hahn, and Wilson. So suppose that A to B is evenly free. And let me also assume B is even. So in particular, I'm assuming this is a map of commutative ring spectra. Then we can compute the even filtration over A of some. Oh yeah, so first let me also let M be an A module. Then we compute the even filtration as the kind of totalization or the limit over delta of a particular cosimplicial object. So let me write something down and then I'll explain what I mean. So we have some cosimplicial object, then we're going to apply this Whitehead filtration that gives us a filtered cosimplicial object. We take the limit over delta that gives us the filtered object. And this is an equivalence. So what do I mean by that notation? So here, if I write M smash over A, B smash over A, bullet plus 1, I mean this cosimplicial object. So we start with M smash over A with B, smash over A with B, smash over A with B. And because B is an A algebra, we have a unit map and we have a multiplication map. So this is actually, yeah, let me put the codegeneracy maps in as well. So the maps are given by M smash over A with eta smash over A with B, M smash over A with B smash over A with eta. This is the M smash over A with the multiplication. That's probably not legible. Sorry about that. Yes. This is the limit over the simplex category. So like this category. So it's a cosimplicial object. Yeah. I'm sorry, simplicial. What's that? Toads. Yeah, sometimes called toads. Yes, sorry. That's yeah. That was the simplest thing to say. Yeah. This is smash over A. Yeah. Yeah, if you say toad, then you have to sometimes be careful about whether your thing was fibrant or cofibrant. And so I like limits because then you know you're taking a homotopy limit because I'm in infinity categories. And so yeah, anyways. It's just a style choice. Okay, so you have this map and then you do the same thing here. Eta smash over A with B, smash over A with B. Smash over A with B, smash over A with eta, smash over A with B, and so on. So So yeah, the maps, hopefully you can fill in this diagram from this. So it's like, if you've seen the atom spectral sequence, it's exactly like the B-based atom spectral sequence relative to A with coefficients in M. Yeah, I guess I should say, let me erase this. So if B has bounded P power torsion and everything is P complete, then you get a similar thing in the P complete setting. So corollary of this is that the even filtration of the sphere itself is what's known as the Adams-Novikov resolution, or Adams-Novikov filtration. We take the even filtration of the sphere. This is the limit over delta of mu smash 4 plus 1. So this is what they call the decalage of the Adams-Novikov filtration. So that, like, you're already passing to, when you take the associated graded, you get the E2 page of the Adams-Novikov instead of the E1 page. Okay. So yeah, let me just also say there's a version, the P complete version. Oops. Okay. So now I want to say how this stuff connects up to some motivic homotopy theory. So okay, so I don't want to go into too much detail here, but just to give a complete story, there is some notion of like motivic spaces over the complex numbers. These are given by certain sheaves on smooth schemes over spec C, taking values in simplicial sets. So they're sheaves with respect to something called the Masnevich topology. And then we want to do some kind of A1 inversion. So yeah, so don't worry too much about this. This is like some analog of spaces in schemes, and also regular spaces also sit inside of here. And then we can form the motivic stable homotopy category by taking P1 loops and taking the limit. So to make sense of this, you have to use infinity categories, but there's other models for it as well. But yeah, so this is some version of spectra for schemes over the complex numbers. And it turns out that like it's kind of a surprise that this is actually closely related to the even filtration. And we will actually use this in a kind of key way. Sorry? Oh, yeah, thank you, yes. Yeah, that's right, A1, yeah. Okay, so I'm gonna attribute this to Georgi Isaacson. How's that, Enrica? So the way I'm going to state it is also using this result, and there's another version of it due to Strikovsky. So if you look at modules over the even of the sphere in filtered spectra, and this turns out to be equivalent to so I need to say cellular here, but maybe I don't want to go into too much detail about that. So you can talk about like CW complexes in this category. And then I want to take modules over the P-complete motivic sphere. So there's some motivic sphere living inside here. It's the symmetrical unit, and we just P-complete. Okay. So this is a really powerful theorem. As I understand it, it comes down to some algebraic fact where if you look at the E2 page of the motivic atom spectral sequence, then this is just given by taking the usual one and then adjoining some generator. And that was sort of the initial observation that led to this. And then there's a separate theorem of Georgi, Long, and Zhu, which says that if you look at the associated graded, sorry, this is in graded spectra. So this turns out to have a nice algebraic characterization. So this is equivalent to actually the stable derived category of it just modules over the P-complete sphere. Yeah.
Your spectrum is
Yeah, exactly. Yeah. Okay, so then this is equivalent to the stable category of mu star mu comodules, or sorry, BP star BP comodules. And we're just going to look at the even ones. So what you do is you can take like the derived category of BP star BP comodules, and instead of inverting quasi-isos, you invert like X equivalences, and that's how you form this category. Okay. So yeah, this is a cool fact. There's one kind of concrete way that we will use this. So in particular, you could look at BP star BP comodules sitting inside here. It turns out that's the heart of some T structure on this, but we'll not go into that. But if you take some BP star BP comodule, that's going to correspond to something here. Yeah, and in fact, this is a monoidal equivalence. Yeah, sorry, I meant to say that earlier. So it sends algebras to algebras as well. So if you have some commutative algebra in BP star BP comodules, that corresponds to some commutative algebra in Guryev S modules. So the corollary is there exists a commutative Guryev S module, which I'll call Guryev. I'll remove the P, but then go mod P through Vn, corresponding to the commutative algebra, BP star mod P to Vn in BP star BP comodules. Okay. So this is really remarkable. We talked earlier about how in spectra, you may not always have these Smith-Toda complexes where you just quotient by P through Vn. So for example, at the prime 2, S mod 2 in V1 doesn't exist, right? You don't have a V1 to the 1 self-map on S mod 2. And moreover, even if those did exist, they're not going to be E infinity rings. They're not even going to be E1 rings. So, so this is pretty nice that in this world, we actually do have kind of like commutative ring spectra, which correspond to these honest Smith-Toda complexes. So that's really useful. And yeah, let me fit this over here. So given a BP star, or sorry, given a Guryev S module, we're going to write X mod P U1 through Vn for X tensor over Guryev S with Guryev S mod P through Vn. So it's the same thing you would do in spectra, although now we're using this fancy day convolution tensor product and doing it relative to Guryev S. All right, so this is the story of the even filtration just in the kind of usual sense. So far, there hasn't been any connection to THH yet. So rather than kind of, is there a question? Oh, yeah.
What is the corresponding modules from there to the stable homodule category? Like, is it close to like the bi-graded homotopy group of like whatever you have constructed here?
Wait, sorry. So you mean like given a general X, or this particular one? What's that? Yeah.
That's like the graded.
Yeah. This thing. Yeah.
Is it a bi-graded homotopy group?
Its homotopy groups are bi-graded. Yeah.
Same as X over
Yeah.
Module P, P on.
Yeah, exactly. That's true. Yes. So so when you take graded spectra or filtered spectra, you take homotopy groups in that category, you have kind of two different spheres there as well. So you also have bigraded homotopy groups. And maybe, for example, if you take pi star of Gur-Eve S of the sphere, that's going to be X. Let me do the P-complete version. That's going to be X in BP star BP comodules of BP star BP star. So there's a secret second grading here. Yeah. Yeah, thanks for the question. Yeah, and if you did this one, it would correspond to just PP star mod P through Vn here. Okay. So I don't want to go through the general definition of these different filtrations in all these different contexts. Let me just say that there are variants of the even filtration in these different categories. So for example, in functors from S1 to spectra and cyclotomic spectra, that give us filtrations. So there's going to be some kind of fill moat. See how do I want to describe it? So there's going to be fill moats of THH of A, fill moats of TC minus of A, fill moats of TP of A, and fill moats TC of A. So when A is a, so we just need an E1 or a, let's say, associative R algebra for some commutative ring spectrum R. So in the case of this one is actually just defined as the even filtration over THH of R of THH of A. Yeah. Here you do the same thing as you did with the even filtration, but then you apply the homotopy S1 fixed points, and you take the limit in the category of functors from BS1 into spectra. Here you do the same thing, but you apply the take construction and take the limit in functors from BS1 to spectra. And then here you take the equalizer of maps from maps from the homotopy fixed points to the take construction of con and phi, and then you take the limit over all maps from A to B, where B is cyclotomic. And you do this all relative to some R. So, so there is some kind of general formula for this, but I'm only going to talk about this in the case when R is an MU algebra, and then we can use a similar kind of descent theorem to what we had before to reduce this to some kind of explicit cobar complex. So let me just state what the explicit cobar complex is in each of these cases. Yeah. So you can take that as a definition of these motivic filtrations, if you like. So let A be an associative, let me just say an MU algebra, then we can define Filmot THH of A. There's going to be, I'm going to start implicitly decompleting here. Sorry about that. So really, you also need to do the kind of p-complete version of these filtrations. So then this is going to be limit over delta of tau going up to 2 star of THH of A over mu smash bullet plus 1. So let me say what I mean by this. So that is shorthand notation for something we already saw. So this can be defined as THH of A smash over THH of mu with mu smash over THH of mu bullet plus 1. So this is that same explicit cobar complex we had before. And then for these other filtrations, we can do the same thing, but we're going to apply TC minus TP. There's an issue with TC, but let me just save that for now. So we also have TC minus of A, limit over delta, TC minus of A over mu, smash bullet plus 1. So it turns out that this is a kind of relative THH. So this was also what was called THH over mu smash bullet plus 1 in previous lectures. So this is the same as this, but it just gets to be too much in this superscript. So let me not use that notation. Okay, and then the motivic filtration TP of A is the same thing, but now we have TP. Okay. And now for TC, we run into a little bit of an issue. So you would like to say that this THH relative to mu is just cyclotomic. So you can just apply TC to that. However, you need a special property on your base in order to show that THH of A over that base is actually cyclotomic. So what you need is the map from THH of mu to mu to be a map of cyclotomic spectra. So that's what we call, so if we have a map like that, that's a map of cyclotomic spectra, we say that mu is a cyclotomic base. So at least presently, we don't know that mu is a cyclotomic base, although this has been announced by Alan Yuan that he has a proof of that. But until he puts that in print, let's not assume that. So there is a fix for this, though, which uses these more abstract versions of the motivic filtration. So you just replace the map from THH of mu to mu with another map, and then things work. So let me state it this way. So there are filtered maps on in phi from modes EC minus of A. So let's say we have the same hypotheses as over there. So again, I'm implicitly p completing everywhere. So, and these converge. So if you take the colimit, they converge to the Connes and phi of Nicolaus and Schulze that we talked about last lecture. Okay. So really, the main thing that you're using is that these definitions are independent of which evenly free map you chose. So let me just say, so the proof sketch is going to be you replace PHH of MU to MU with another map, PHH of MU to THH of MU over MW, where MW is another Helm spectrum that was constructed by Hahn, Rexed, and Wilson. So what is MW? So the W is for Wilson because it's related to Wilson spaces. And so what you do is you take loops infinity of suspension 2 of MU. And then you have a kind of Connor-Floyd, there's a particular choice of map that you can use to map to KU. It's a certain orientation. And then you note that this is going to be equivalent to BU by Bott periodicity. And then you can map to BGL1 of the sphere, and you take the Helm spectrum of that map. Here. This one? Oh, sorry. There's filtered maps, Connes and phi. What these maps are? Yeah. So I defined them in my first lecture, but just it's okay. But so yeah. So Connes. These are going to converge to maps on TC minus and TP. Connes is there's always a map from the homotopy fixed points. So that's the definition of TC minus to the Tate construction. So the Tate construction could be defined as the kind of cofiber of the norm map. So you always have a map from this to the cofiber. And this is the TP. This is the TP. And then the phi map. So the phi map uses the cyclotomic structure. So THH is cyclotomic in the sense of Nicolaus-Schulze, which means we have a map from this to the CP Tate construction. And then we apply HS1. And, yeah, so maybe I'm actually missing a hypothesis. Yeah, sorry. So A should be actually a connective MU algebra. Oh, yeah, I'm glad you asked because now I can fix that. So when A is connective, we showed last time that this was equivalent to TP of A after P completion. And here I'm implicitly P completing. So what I'm doing is I'm taking the cyclotomic structure map and taking the S1 homotopy fixed points. And then P completing. Thanks. All right. So yeah, getting back to this MW, I just wanted to kind of advertise this spectrum as a kind of side story because I think it's an interesting spectrum. So one thing that's nice about it is is the following. So mu has this nice property that it's built out of even cells as a spectrum. So you can use the fact that BU is kind of built out of even cells by like using some kind of, yeah, I mean, this is a kind of classical thing. And then you can use some stuff that Samik talked about to show that mu is then built out of even cells. And then because we're taking Loop's infinity of that, here we see that this is actually built out of even cells, even as an E infinity ring spectrum. And that's a pretty useful fact. That allows you to prove that THH of MW, or that MW is actually a cyclotomic base. So there's some kind of obstruction theory for, in some sense, to show that something's a cyclotomic base. And if you're built out of even E infinity cells, then the obstructions vanish. So that's one thing. And it means that anytime you have a even E infinity ring, you get a map of E infinity rings from MW to that. So that's how you get this map from MW to MU. So yeah. I think Connes and Wilson usually try and sweep the spectrum under the rug, but I find it kind of interesting. So. Okay. Yeah, so then we can define homot TC of A. So again, let A be a mu algebra that is connective, let's say. Then we can define this as the equalizer of these filtered maps. Right, and then, yeah, so this has associated graded. Remote of TC of A. And now we're going to call this associated graded the symptomic cohomology of A. And in the case of TP, this is the prismatic, well, it's really the Nygaard completed. Let me not worry about that. Prismatic cohomology. Okay. All right. So yeah, so when I say symptomic cohomology, this is what I mean in the case of an MU algebra, for example, and similarly with prismatic cohomology. So of course, Connes and Wilson did not invent symptomic cohomology and prismatic cohomology. This existed before them. So in order to call this symptomic and prismatic cohomology, they had to relate it to what was called symptomic cohomology and prismatic cohomology before. Oops, sorry. So this recovers the symptomic homology and prismatic homology of Bott, Morrow, and Schulze. So Bott, Morrow, and Schulze in around 2018, 2019 defined some kind of symptomic cohomology and prismatic cohomology in the setting of quasi-symptomic rings. So this is this kind of ring I discussed earlier. And what we saw, right, was that given a quasi-symptomic ring, you can produce some other ring such that when you take THH of your quasi-symptomic ring, it maps to the other THH. And so the target is going to be even, it's going to be cyclotomic, and it's the map is a evenly free map, right? So that tells you that using their kind of descent theorem, then you can kind of recover basically symptomic cohomology and prismatic cohomology the way they defined it, because they defined it using some kind of, I mean, they use some kind of algebraic geometry, and so you need to just know that you have some nice cover in their sense, and the kind of cover I constructed was a cover in their sense, so in the kind of quasi-symptomic topology. So yeah, so that's really nice. And maybe let me just also say, the symptomic cohomology goes back even further. So the first place that I know of where symptomic cohomology was defined was in work of Fontaine-Messing in the 1980s. And that had nothing to do with THH, the way that they defined it. And Bott, Morrow, and Schulze showed that their definition using THH recovers this original definition. Yeah, and it's symptomic cohomology is really nice because it's kind of like it's some kind of generalization of like Étale cohomology and de Rham cohomology and crystalline cohomology. So all these other kinds of nice cohomology theories and p-adic geometry can be recovered from symptomic cohomology. So I just want to remark that all of these different kind of motivic filtrations are also modules over the even filtered sphere. So we can also consider the mod E V1 through Vn symptomic cohomology of an MU algebra, which would be remote star TC of a mod E V1 through Vn. And yeah, maybe, and similarly, we can do Germote. Well, let me just say F of a mod P V1 Vn for all those functors we cared about. So for F and THH, TC minus, TP, etc. So all of these things are modules over the Germote or Gur-Eve of the sphere And so we can tensor over that with the mod p through the n thing. And moreover, if A is an E2 MU algebra, then these are also going to be rings. They'll be E1 rings. Okay. Okay. So I just want to set up some notation. So given, so X in pi n W, let's say M is a graded spectrum. We say X is in degree n, and atom's weight 2W minus n. So in particular, for all of these graded spectra that we're considering here. And we have a motivic spectral sequence which goes from Gromot, just say F of A mod P through the n. Let me even, let me be more precise. Goes to Gromot. Oh, sorry, no Gromot, just F of A mod P through the n. So this will be the case whenever S mod P through the n exists as a spectrum. And this will be the case for F, for all of our F that we consider. For example, THH, TC minus, TP, TC. So we'll always call these a motivic spectral sequence, and then we're going to actually grade it. This is the E2 page, and we're going to kind of grade it in terms of this degree in atom's weight, n and 2W minus n. Okay. So so we talked a little bit about how we have these S1 homotopy fixed point and Tate spectral sequences. You have some analog of that here too. So you have a kind of something like a S1 homotopy fixed point spectral sequence computing Gromot of TC minus, and something like a Tate spectral sequence computing Gromot of TP. Let me be explicit about it, even though it's a bit of a mess, but there are filtered graded objects. So what we're going to do is we're going to take the limit over delta, and then we're going to apply tau greater or equal to or sorry, do I want to do it? Yeah, no, we're going to do H pi star. Sorry, so let me do the Germot one. Sorry about that. So we'll do H pi 2 star. And then we'll take THH of A over MU, smash bullet plus 1. And then we're going to apply Whitehead filtration here. And then we're going to take homotopy fixed points. Okay. So that's a bit of a mess, but there's some filtration. You do something similar for TP. This limit over delta H pi 2 star tau gradient with the star THH of A over MU bullet plus 1 TF 1. Okay, so we have these filtrations. So we have these filtrations and associated spectral sequences. Which, so Hanrex and Wilson call them algebraic T-Bachstein spectral sequences. Just say it that way. So they go from Germot THH of A, Angelini generator T, to Germot EP of A. Sorry, this is TC minus. And then we have a similar one. TP. And so on the E2 page, it's given by inverting this class T. And on the abutment, it's given by the canonical map. So here, T is some class which is in tri-degree -2, 0, and then 1. So this is the degree. This is the, or sorry, yeah, the degree. This is the atom's weight. And then this is what we call the Nygaard filtration. So that's more for historical reasons. When this is actually a quasi-symptomic ring, then this corresponds to something that, of course, that people call the Nygaard filtration in that context. And then the classes, if X is in I star Germot THH of A, then it's going to have some atom's weight and some degree. And the tri-degree of X is going to be given by N 2W minus N, and then it's going to have 0 Nygaard filtration. So yeah, this is like it's coming from the cohomology of BS1 or CP infinity, which we think of as being in -2 because of homological gradient conventions. So yeah. Oh yeah, it's maybe not, maybe it's easy. Okay. So yeah, in my last lecture, I'm going to use these spectral sequences to do an explicit computation in the case of truncated Braun-Petersen spectra. So I have 10 minutes, so let me just give a kind of, it's going to be kind of one step in the proof, but It's also, I don't know, it's its own little topic, so it shouldn't take too long. So so first I'm going to need to let Gromot of THH of A, say A is an MU algebra again, PCP. This is going to be the limit over delta of tau greater than equal to 2 star. It's the same kind of thing, THH of A over MU, smash bullet plus 1. I may want to assume that THH of A, that this thing is p-torsion free and even to get this to work out nicer, but let me just not worry about that for now. Then, so suppose Vn plus 1, let's see, yeah, Vn plus 2 map to 0 in the composite. So we can take BP to MU. Remember, we're implicitly P completing. And then we can map to A. So there's these generators. BP has these generators. Let's Z localized at P, V1, V2, and so on. And we ask that the Vn plus 1s through Vi, these higher VIs go to 0. Then we can show that Gromot of TP of A mod P through Vn plus 1 is going to actually be equivalent to Gromot of THH of A, TCP, mod E through Vn. So this is what Hahn, Rexed, and Wilson call the useful isomorphism. So they just proved this in the case when A is the atom summand. But their same proof basically works this level of generality. So the idea, you just sketch the proof. So you start with THH of R, MU smash bullet, let's say smash Q plus 1. So that's going to be an MU module. And if we take the S1 take construction of that mod P through Vn plus 1, or sorry, mod P through Vn, well, so this part is not so important yet, but so more generally for any MU module, you can take this and smash it over MU TS1 with MU TCP, and that's going to be equivalent to THH of R MU smash Q plus 1 TCP mod E through Vn. So yeah, so far what I've said here works for any MU module. You could put any MU module here, and that would work. Yeah, here maybe I want MU to A to be surjective. Let me just assume that as well. Sorry, what's that? Okay, so yeah, so then we have this this equivalence, and yeah, so then we just need to say, well, right, so given a, yeah, so this is true for any complex oriented thing, but let me just say for MU, the homotopy groups are given by MU and then power series on T, or not power series, Laurent series on T. And if you do this, the CP take construction, you take the same thing and you mod out by the P series on T. So essentially what we're doing is we're taking this and then modding out by the P series on T. And yeah, so then we just need to show that, so note, and this is the part that I'm going to be sketchy on, but or at least one part I'll be sketchy on. So if you look at the ideal generated by the P series, then this is going to be the same as the ideal generated by Vn plus 1 mod E through Vn. So the idea is that the P series you can write as P times T plus V1 T to the P plus V2 T to the P squared. Maybe over the formal group law. And then, so the nth term, once you kill P through Vn, is going to be P through Vn minus 1 is going to be given by Vn times some unit. So yeah, so that's kind of the key fact. And then, so here we have this equivalence, and then we just identified this quotient with the quotient by Vn plus 1. So
that S not P but AM exists.
no, so I'm using the fact that it's an MU module. MU module. Yeah, yeah. Yeah, and then, yeah, so then this tells us that this is this, if you do mod P V1 Vn and then mod the P series. So this statement is the same as saying this is equivalent to THH of, I switched from, at some point I switched from A to R, sorry about that. Okay. And then this we identified with THH of A mu smash Q plus 1, ES1 mod P through Vn plus 1. So that's how you prove this. And then then you have to use descent. Or I guess maybe I should just say not even descent. It's really just like passing to the E2 page. So you can think of this explicit Kobar complex as like the E1 page of this spectral sequence, and then so then when we pass to the E2 page, we get this. Yeah. Okay, and I think that's all I'll say for today. Thanks.
Any questions?
Say that again? Yeah. Yeah. I mean, I guess I don't know the classical story so well, but I know that like if you had that, if this was even, then this filtration agrees with what people used to think about, but it's not something that I have thought about personally. Oh, it's the filtration. Yeah. So the Nygaard filtration, at least from my perspective, is this filtration I had here, the plus thing. Just do the TC minus version. Well, A is an MU algebra. Then it's where we take H pi star pi equal to star of THH as A, HS1. So yeah, from my perspective, this is the Nygaard filtration. And then I'm happy that people thought about it earlier and had a nice name for it, but I haven't thought about their perspective on it. Yeah, sure. Yeah. Yeah. So it's so Tor amplitude is like if you take the derived tensor. So if you have some m, let's say, then it has Tor amplitude in 0, 1. If you take this over, let's say it's an A module. Now I'm writing way too small. Let me write this somewhere else. So if M is an A module, then you ask that M tensor or derived tensor over A with L with N for any, or that this is inside 0, 1. It's like when you compute Tor, it's like just at 0 and 1 for any A module. N. Yeah, and that idea goes back to Quillen. So Quillen had this way of characterizing like regular rings and smooth rings in terms of the cotangent complex, and then so this is kind of generalized in this work.
Any other questions?
Oh, sorry. Yes, it's trivial action. Yeah, thanks. Yeah. So the connectivity was used just in the only time I was using connectivity was to show that this HS1 was equivalent to TP of A. So it's true that you don't actually need it. Yes, THH of A being bounded below would suffice. Yeah, but the easiest condition to put on A such that THH of A is bounded below is to say A is connective. There are other examples though, like there's like this thing that's like the image of like the -1 connective cover of the K1 local sphere, which happens to have the property that its THH is bounded below. But I don't think it's true that every -1 connective spectrum has bounded below THH. So yeah, you're right that THH of A being bounded below is the key thing that's used.
Any further questions? If not, let's start. Thank Gabriel again.
Yes.